Good morning, ladies and gentlemen. My name is Michael Zuiv, and I come from Tallinn, from Maritime System Institute. And my talk is dedicated to assimilation of data and observed from satellite. And this data is temperature and sea surface salinity. What is data assimilation? Why do we need that? Obviously, model forecasts ocean state, and we don't know what will happen tomorrow, how precise it will be. And our task is to make these forecasts as accurate as possible, and observations can help with this task. And if we would like to have that many observations, that in cloudy days we have as many as this or even less. So the question is how we can use few observations and get the best results possible with that many. Our model is HBM, which works for entire Baltic Sea and portion of North Sea, and my setup is about Estonian waters or northern eastern Baltic Sea, and resolution is half of nautical mile, and we have taken 5 years of model data and try to improve the forecast. So the first idea is to interpolate the observations that we have and extrapolate to other empty areas, or use the covariance between 2 points. But as you can see, with increasing distance, covariance can increase, which is not logical. So that creates problems for optimal interpolation and other methods. And we applied empirical orthogonal functions. We have taken the data, averaged over 1 day, so we had daily data. Then we created a very coarse grid to minimize the number of points. So instead of 200,000 points, we get only 744. Then we have taken the covariance matrix for each of the pair of the cells. So this is a historic time series for 5 years of each 2 cells. So we get the matrix, and then we calculate eigenvalues to satisfy a condition that's being multiplied by identity matrix and subtracted from covariance matrix, it will give 0. And this matrix can help us to improve the forecast. So the diagonal of this matrix can help to calculate amplitudes of different modes, the strongest and with diminishing strength. So for example, for the temperature, as you can see, blue and red lines are the strongest amplitudes, which explain the seasonal variation, and weaker signal is third, fifth mode. And the same with salinity. accounting for upwelling and mixing. And off-diagonal elements of the same matrix are mapped so they can show the spatial influence. As you can see, the temperature, the strongest signal is seasonal. Then it's cooling of the shoal water, then it's upwelling, and then it's transverse separation. So this is the strongest modes of temperature and salinity. And subtracting these modes, the strongest signal, we get only deviations, and covariance between them can help us to build the proper covariance matrix and use it with, for example, 3D bar assimilation. And as you can see, instead of too hot shoal water areas, we get nice and beautiful, very realistic results. To conclude, I can say that empirical orthogonal functions can be used to extrapolate sparse data, like from ferry box to entire region. They can be used for subregion. They have small errors, and they have clear physical interpretation. They are statistically well justified, and this is the first step for improvement of data assimilation for our model or operational setup. So if you have any questions, please feel free to ask.
Thank you.
Let me ask, because I lost the beginning of your talk. Could you just repeat? Did you base your analysis only on the modeling results, or you somehow use the real measurements, spatially distributed? For example, salinity.
Thank you. This is a very good question. Yes, we didn't use salinity measurements in the entire basin. So for purposes of this research, we used only model data in order to calculate the covariance matrix. And then, after that, we can use these results for assimilating the satellite data, ferry box data, buoy data, and so on. So, answering your question, you were completely right. It was only model.
Other questions? Yes.
So, as I understood, you're using a 3D bar for the assimilation of the satellite data, for example, into the model. Is that right?
Yes, you're completely right.
My question is for forecasting. With 3D bar, you lose the time component. Wouldn't it be advisable to use 4D bar in order to also get the time component into the forecast?
Thank you for your question. As far as I'm doing this research, and I'm still a PhD student, so the 4D VAR will be the next stage for me. So first I need to understand 3D VAR and how to use it properly, and then we will proceed with 4D VAR. Yes.
No. I have a feeling that it's a very powerful result, this principal component you found. Because this principal component and spatial distribution of salinity and temperature could be attributed to real, very important physical process. If you will go to the slide, could you go through this principal component and tell once more where is upwelling, where is other? Yes. Because as I understood, any real field of, for example, temperature,
yes,
could be linearly calculated from this principal component with weights. This,
Yes,
am
this
I
is,
right? Yes.
yes, this is composition of different modes,
Yes.
like weights, for example.
So,
And-
so it means that these different modes are very principal, and they could show us the clear effect of different processes. Could you go through just and tell this is because that, because that?
Yes. So the first for temperature is the strongest one. So it has 93% of total variability, and it shows the seasonal variation. That's why we know that in the summer it's everywhere is warm, and in winter everywhere is cold. So then this is like less than 10% variability is cooling and warming of shoaling areas during
Season, different seasons.
during spring or autumn. Then we have more frequent, this is less than 1% variability. Near Finnish coast, we have stronger and more frequent upwellings. And this one is less than 1% of variability, which means the circulation between Gulf of Finland and Baltic proper.
And for salinity?
For salinity is very similar, yes. So this one is like 75% of total variability, which means that normally the saline water is near the Finnish coast. Then flow of the Neva River and its water, fresh water, going along the Finnish coast is, yes, that's like less than 10%. And these are like 5 and 1, which is cyclonic circulation and anticyclonic circulation of the water.
Thank you. Yes, okay. Yes.
As far as I know, I get that empirical orthogonal function and model data, yes, and you apply
Yes.
empirical orthogonal function to those model data, yes, and you get your result. Yes, that's right.
Yes, you're completely right.
Yes, and so the data are not real. Am I right? They are modeled.
Yes, they are modeled.
Okay.
Yes.
I mean, in the future, you are going to compare the real data and with the model data, and how somehow, I mean, the aim, the purpose, and the point of your job is to checking empirical orthogonal functions, or and this is my question.
Yes, thank you. Very good question. If I would use like these observations for orthogonal functions, we wouldn't have that many values and they couldn't be reliable. That's why we tried first with the model, because the model is rather good and the errors are less than half a degree Celsius for temperature. So it describes physics very well. That's why we use the model, because it has 100% coverage. And it is a good starting point. So it's better than nothing. And then we can gradually improve it as we get more data and more observations. And in any case, we will compare this and improve the assimilation algorithm.
So the aim is to find out those regions that we have no data from that places, that regions. I mean, yes.
The goal is to be able to use very small amount of observations from like ferry box or in cloudy weather, because for Gulf of Finland and Estonian waters is a very big problem, and being able to use them anywhere in the model domain.
So to extend the information from one line of ferry box just through whole Gulf.
Exactly, yes. not globally,
Okay, but
on some
in
regions.
principle,
Yeah.
If you compare your modeling results with and without assimilation, if your model gives a nice physics, why do you need to use assimilation?
Thank you. Yes, that's the question of data assimilation as a whole. But still, yes, we have the model is very good, but it is no end for improvement, and that's why we need to make the forecast, especially operational, more precise. And it could be used, for example, in other setups, like for North Sea or Danish Straits,